Okay, let's look at the schedule from Canvas. I can tell that last night someone were struggling, so I delayed the deadline for one more day. So I was gonna do today for the VGA tutorial on my website, and there's for the lab it's due next week, so it's fine. And there's another thing for students in the VLSI class. Please sign the TSMC NDA. So I didn't make it required point, but you can see it's 0 points. But the thing is two. I'm gonna give you 2 out of 0, so which means that's how I make it not mandatory, and it's a bonus points. You know what I mean? So the denominator is 0, but the numerator is 2. So that's how I add a bonus points to a grade. So if you don't do it, there's no penalty because the base point is 0. Okay. But since if you want to work on that course project in the VLSI class, you just have to sign an NDA. And whenever you open up the NDA, it says it's a top secret of the company, blah blah blah. But even though it's a 20-year-old technology, but still it's some sort of secret. You don't want to disclose it. So all the standard cell libraries, like what you guys did in the VLSI class. Remember when you lay out all the individual gates and multipliers and not multipliers, sorry, as adders, different flops in the future. So all these ones you guys laid out in the class will be used for a larger scale circuit like the ALUs and all these kind of things. So these sub-modules are called standard cells. So these standard cells can be reused for millions or billions of times on the chip. And how you guys laid it out, and the space between all the transistors and the wires, the metals, how you routed all the metal 2, metal 3 wires, are secret for your project, right? So you don't want to disclose it if you're working for a company. You know, sometimes it matters, okay? So TSMC's engineers laid it out using their technology, right? Since they fabricated the chips, so they know the gaps and distance between the traces and also the height from rail to rail. So they defined it by themselves because they know that's probably the best way to define the height, and it gives them the best yield of the chip. So that's why it's a secret. Okay. So once you receive all these standard cell library packages in the zip folder, make sure don't disclose it. You'll be in trouble if you do it. Okay. And that is why this program in Ford's College is so unique, because it takes so long and so much trouble to get everything signed and approved. So it's part of the reason, it's part of probably 1 out of 100 reasons why other institutions are not doing this for you guys or for students. We still have time, we still have about 2 months. Okay, so let's sign it. And probably, hopefully towards the end of March, we'll be able to get all the standard cell libraries, and we'll be able to start laying out in cadence, okay, the chips in cadence. You can see the bonus points for today is about 3 points. Cannot be 35 points every time. It's gonna add your grade to like 1,000 out of 100 to the end of semester. I was not planning on doing a bonus point last time, actually. I was trying to give you guys a quiz, but a lot of students didn't show up, so I was thinking, let's do bonus points. Okay, so it's not hurting your grade. Okay, as a bonus point in the future, moving forward, it'll be something like a 0.1 for each problem. Can be 30. But eventually, everybody's getting a AAA, like AAA. We just don't have that grade available. That's not going to work. Okay. Hopefully this helps you guys a little bit to pay attention during the lecture. Okay, let's take a look at the problems. There are 6 problems, and pretty simple. Open this tutorial, solve the core. So I do need to explain something because it's a little bit confusing. So this one is not available from the textbook since we have 2 textbooks, right? If you look at the syllabus here, What are the two textbooks? One is from the Turkish guy. Another one is from a Taiwanese guy, but I think Peng Chu teaches in, is that Cleveland State or Ohio State? I forgot. What are the two textbooks? Yeah, these two, right? Digital System Design, IPGA. So I'm showing these to you guys is because I know a lot of you guys didn't purchase any of them. So the first one is the one we follow. Most of the tutorials follow the examples from this textbook. I think this is a professor in Turkey. Another one is Professor Peng Chu, is a Taiwanese, but he teaches in Cleveland State or Ohio State. I forgot the name of the university. But this is a really popular textbook for IPGA design. And he probably wrote this book maybe 10, 12 years ago. And by the time Basic 3 board or the Arctic 7 chip IPGA was not released yet. So everything here is based on the, I forget the name of it, Spartan or something. Oh, Spartan 3 and a different IPGA platform. And by the time he wrote the book, the software core we are using in this class was not available. And so if you click, just open up this tutorial, you can see the one we are using is called KCP-SM6. That's a relatively newer core, I think released probably in 2014. But when he wrote the book, he used the older one, which is KCP-SM3. And in his textbook, he provided the full code for including the assembly and the core and not this one, and the structures of the core and a lot of information. However, if you just follow whatever he put into the textbook, it won't work. And I was trying to find out information from any website, any online resources. I couldn't find a existing code or configuration for the core and we can use for the Arctic 7 IPGA chip we have on the Basic 3 board. So eventually I modified a lot of things of the core's Verilog file and also the main.v file, and eventually make it functioning. And it's probably the only one on the website or anything open source that's provided to the public that is functioning for the Basic board. Okay, so let's start from the top. KCP-SM6 has a name, and you can find the name from the tutorial. You can see it has about 15 A, B, C, D, E, F. So it's 15 or 16 registers, and you can write the data into the RAM, and do all the calculations. So now the first two questions are answered, right? The second question you can find by scrolling down, I think. Let me try to find it somewhere. Constant coded programmable state machine. Yeah, another reason for that is so K pronounced as K, but actually start with C is constant, and the name of the guy who designed this core. Oh, you don't have it. Or missed too many bonus points, right? Look at this guy. Official user guide. Ken Chapman. Okay, Ken Chapman. I think he was an engineer at Xilinx. So Xilinx was acquired by AMD. Okay, so now it's AMD company. So you can open up this data sheet to find out all the instructions of the core and a lot of information over there. But I just found out another one which is very useful, and the original data sheet didn't include many of the details of the wiring and everything. It could be useful sometimes when you're programming the hardware. which is this link. I'm going to include this link to the tutorial after this lecture. I just found it this morning. I was searching for some of the information for the ports, and eventually I found this document. This will be very useful. I'm going to include a link to the tutorial after lecture, okay? And so how do we program it? Since this is a very hands-on class, right? How do we program it? So first, the core is a .v file, okay? If you download, let me show you where the link is. It's a long tutorial, okay? Download the KCP SM6 release 9. Look at the date. It's September 14th, 2014 September, okay? So this one, click it. Okay? So since you have registered, you have downloaded the Vivado to your laptop or anywhere, so I assume that you already registered account with AMD. And it probably is going to ask you to sign in, and eventually you will be able to download this release revision 9. Okay, it's a zip file, and eventually you can open it up and you can see a bunch of folders and files inside, like these ones. And what are they? Okay, so if you see this KCP SM6.vhd, that's a VHDL file of the core, and that's a different version compared to ours, and we're not going to use this one because this is for VHDL. It's a different hardware description language. So this semester we're not learning that. We are just we only care about the Verilog. So is there a .v version of it? So it's not in here. Then click Verilog. And you'll see there's a KCP SM6.v. Okay, so that's the core. That is the core. Someone's making notes. Oh, find the answer for this question. So this is the core. Okay, .v, that's the core. That's the CPU. And KCP SM6 _ design _ template. What is this? Open it up and take a look. It has a lot of examples of the top module. Imagine in the future when you are programming, we are making a system on chip or a microcontroller. You have the core. Okay. Here's the KCP core. Okay. And there will be a instruction memory. It's a ROM. So you need the top. This is how we model it, right? You need the top. So that template.v file is not a file that I can directly use. It provides you with all the examples that I can use to program your top, and we call it main.v. Keep in mind, it's just examples. Don't directly compile it. It's not a functioning .v file that I can directly use. What else do you have in the folder? ROM _ form.v. Keep in mind, don't get confused. It is not ROM.v. It's a ROM _ form.v. Okay? So this one defines the form of your instruction memory. You have to include it into your it's not compile. What's that called? So it's assembler, right? Assembler, when you, let's say compile, it's when it compiles your assembly language, assembly code, instructions, this has to be included in there, so eventually it defines the format of the output. So converts your assembly program into a memory folder which includes that assembly program into a .v file module. It's like a ROM module stores your assembly program in the machine code format, like 1 and zeros. But eventually, it puts all the programs into a .v file. Okay, so how do you define that kind of format to be used for your top? And this is a file that defines the format. So it's a rom_form.v will shape everything into a .v file as a memory file for your SoC, system on chip. So there might be a rom_form.vhd somewhere, but I couldn't find it now. We are not using it, so it's okay. Okay, so I'm going to show you how to compile that memory file in a bit. But you should know that this is not the .v file that I can directly use as a memory, because it's not a memory. It defines the form of the memory. So you use it when you compile it. When you compile your program, assembly program. Okay, let's keep moving forward. And there's another file. If you go back, you can see it's a kcpsm6.exe. That's assembler, similar to the compiler of the C program, right? So assembler brings in that rom_form.v file and also your assembly program, and eventually put everything into a .v form of the memory file that can be directly used for your SoC. So how do we do that? Let's take a look. So you write your assembly code. I'm going to show you some examples. These are step-by-step instructions over here. So first, this is the folder you downloaded from the AMD's website. Okay, this is the folder you downloaded from the AMD's website with all the files in it. And you create a general project file from Vivado like this. New project, just follow the routine. Eventually, you start a new project, and you can see this is all the folders in the project. And you copy and paste the .exe file to the project folder first. That's assembly, okay? It's assembler. It's assembler. And then you get into the Verilog folder, and copy and paste these 3 files into here as well, into the project folder, and make the following changes. And at this point, so in your command line, open up a command line. If you don't have a Windows machine, use a Windows machine. In your command line, type the name of the exe file here first, then space, and followed by your assembly program file. It's a .psm, keep in mind. So you program in Vim, write assembly code in here. It can be, you can start with a really simple one, which is loop, assign a port to it. So this register input is being connected to this port ID, and eventually this output is outputting the whatever value being stored in the register to this port ID. Since they have the same port ID, so they are internally shorted to each other. Eventually, this input, whatever value being stored in this register, will be sent to the output, and then jump back to the loop. So it's going back and forth, it's stacking. So it's stuck within that loop. So whatever, it's a very simple code, and you type it up in your Vim file and store it using a .psm extension. So keep in mind, if you're using your own Windows machine, you have to, let me show this really quick. You have to go to here, View, right? Go to View and Options. Change folder search options, and I believe it's in View. So there's the extension option. So make sure you show the extensions of the files, okay? I think so here. So hide extensions for known file types. So uncheck it. Okay, uncheck it. So eventually, you will be able to change the extension, right? Change the extension of the file and name it as .psm. It doesn't matter what kind of name you gave to the assembly code. So I just use it. I use a program. So assembler is gonna convert it into a prog.v file. Because eventually, the assembler is gonna convert this .psm file into a .v file, and this one can be directly used. This one can be directly used for your program. So in your main, the top module, the top over here is the main.v module here. So you want to change this one to prog, okay, to prog. It's basically the name of the ROM file inside the .v file. So after you do this, you open it up and you look at the module name. So the module name probably is different from prog. So it could be a ROM, maybe just ROM, I think. Doesn't matter. You open it up and look at the name of the module and include it into your main file, so you can instantiate your memory file over here. Okay, to summarize, so all these steps is doing what? It's converting your assembly code into a .v file, because when you are compiling or synthesizing your design, it has to be a .v file, okay? So the instructions are stored in the memory. It's called read-only memory. It's a ROM. It's a ROM.v. So all the instructions are being converted into 1 and 0s of machine code and being stored in that .v file. That .v file includes addresses, right, and also the ports. So it provides the address and it's going to output an instruction. So that's why you need that kind of interface for the memory. So the instruction memory stores all these machine code in there, and the assembler converts it into a machine code and also use the format of the ROM. Remember what's the name of the format of that file, which is rom_form.v. So this file has to be in the same directory as your assembler. So whenever the assembler works with your assembly code, it can directly detect that rom_.v form, rom_form.v file, and converts your program into a .v file, which has a machine code in it. And eventually the product for that sort of operation is going to be the prog.v file, which is your program file with the machine code in it, but also has an interface, right? Like addresses and output, all these kind of ports. It's a memory file. It's a memory file, instruction memory file. All right. And however, the prog.v, that name, the file name, it's not a module's name. So remember, when we instantiate the module in your top, you need the module's name. So how to find the module's name? Just open it up. Right click, open it up with Vim or Notepad, whatever you want to use. Open it up and look at the module's name. And the module's name is going to be ROM something, okay? So find out the name and plug it in to your top. So it's going to instantiate that memory file over here. So I'm not using the DOT or UOT here anymore. So I rename it as program_ROM. Okay? So these ones are just changing the parameters inside that memory file. We don't have to worry too much about it, since I already gave you the answers over here. So directly, so all these examples come from the template.v file, which is this guy. I didn't wrote it up. Nobody knows how to do it. So whoever designed it tells us, hey, you have to use all the example code from the template. Okay. So do this, just directly copy and paste. No, actually, you can directly use it from the template. I have to change all these parameters. So V6, I think it's the Spartan 6 or something type of chip. So I have to change it to 7S. So 7S means 7 series, and that stands for the Arctic 7 chip, the IPGA chip being used on the basic board. So I have to change it to 7S. I have to change this one to from 2 to 1. That's the two parameters you want to change, and you rename it as whatever you want. It doesn't have to be program_ROM. It can be anything else. If you like UUT, DUT, it doesn't matter. Okay, it's just the name of the instance. But this one has to be the module's name in the prog.v file. Keep in mind. So in that case, you can include your stop module of the memory, which is this guy, in your top. So you just need a core. You need the core. All right, the core is a KCPSM6.v, and this is your memory file with all the instructions. Okay, and then you need a bunch of other Verilog code to make the connections, right? Like the wires connections and whatever, sending things to the LEDs and receiving things from the switches. So you can use the resources from the basis board to do some verification or testing. So that's the structure of the design. Okay, and keep moving forward. I think question number 3 can be answered as well. Any questions for the first 3 questions? Okay. Now let's look at the instructions. For most of them are pretty straightforward, but I think there are a couple of them is a bit confusing. For example, compare. Compare. This one. So you can compare a register to a register. You can compare a register to a constant. Okay, these are the parameters you can put into the instruction. So there are 2 flags. These are independent to all these registers. So one flag is called Z, it's a 0 flag. Another one is a carry flag. So Z and C. So when you compare so the register SX to register SY, it could be S0, S1, S2 until SF, right? So you have all these registers can use. So let's say XX and SY, you're comparing these 2 registers. If they're equal, the 0 flag will be turned on. Because assembly code is not as versatile as your C code, right? You can do an if statement. If it is 0, do something, right? So this one doesn't have that if statement. So this instruction becomes very handy. You can see it's basically if statement. If they're equal, you have a flag, right? You cannot do if. So assembly code doesn't allow any like English in there, right? So if they're equal, the 0 flag will be on, and if SX is smaller than or is less than SY, carry will be on. The carry flag will be turned on. So these flags are just 1 bit. Keep in mind, just 1 bit. So think about that in the future. So since you have the flags to be on or off, can be 0 or 1s, in order to find out the values and the comparison between the registers. But keep in mind, you don't have an if statement in the future, right? So for any code following that. So how do you do any of the jumps and branches and other kind of operations? Compare is 1, right? Compare is 1, but eventually you cannot do like if Z0 or if C is 1, do something. Okay? So here comes the jump instruction. Yeah, very limited ways to do things over here with assembly. It can be really tedious. See here. This is one of the ways to do it as a replacement to the if statement, and with all the conditions you can use in the C. So jump NC, what does that mean?
It would go to.
So not 1. So for when C is not 0, not 1, right? NC, N means probably not, right? So it's not C means not 1. So when there's no carry, jump to here. So that's a replacement to the if statement in the C language. So when C is not 1 means C is 0, right? Means no carry. Then jump to AAA. So AAA is a label that you can put in front of the code, like a loop or something, like I just showed you. Let me show you here. Like loop, right? It's going to jump to this location or address. So we'll compare the two registers. The easiest way to remember this is doing a subtraction, okay? Because you can see when it compares SX and SY. Okay, so when SX is less than SY, you gotta carry. Okay, so which means when SX is smaller than SY, if you do a subtraction, it carries out because it's not enough to subtract from SX to subtract SY from SX. Right? So you can always imagine that you are doing a subtraction. It's SX minus SY. If SX is less than SY, it carries out. So C becomes 1. Does that make sense? So when you look at the problem over here, problem number 4. Load means it's loading that hex number, which is 005. It's 05. It's an 8-bit number. It's a hex number. So 05 to S1, 05 to S2, and compare. You can imagine what? Subtraction, right?
Yeah.
S1 minus S2.
0.
So Z equals what?
1.
C equals what?
0.
Yes. So ZC is what?
1.
ZC combined as a hex number is what? Even though we're not combining them, but ZC is what?
It'd just be 1.
Oh, just combined, right?
Yeah.
It's 0, 1, right? Oh, no,
1, 0.
1, 0.
Yeah.
Okay? What about number 5?
It'd be 0, 1, right?
0, 1, why? Because first,
They're not equal.
they're not equal, so 0 flag shouldn't be turned on, right?
Yeah.
So 0 flag is off.
And then also it's like.
Also, it's last, right? So last, which means subtraction carries out. So C will be 1. Z will be 0. Okay. What about the last one? Let's look at test. What does test do? It shows so the data sheet, very nice. It shows you a schematic of it. So it looks like it's doing a bitwise AND operation. Okay. So if you look at the instruction here, it explains you how things work, and because the problem on the paper is doing a test S1 with the hex number 01, it's the constant, so it falls into this category, right? KK means constant. Okay, so SX, XY is a register between registers, testing between registers, but this one is the test between a register and a constant. So it's doing a bitwise AND operation like this, right? So see SX and KK, it's basically a bitwise AND, and eventually it assigns the 8-bit output to T. So T is another flag. It's the test, it's just for the test instruction. It's the flag. It's 8-bit flag. So if T0, then the 0 flag will be turned on. Okay. So in that case, how many 0 flags do you have in the CPU? Just one, right? So you basically are reusing that 0 flag in between different instructions. Keep that in mind. The same for the C as well, for the C flag as well. There's just one C, one Z, and one T. Okay. So when you are doing some checking for the Z and C's, make sure that other instructions are not affecting the results of the previous one. Just keep that in mind. So for this one, is T0 or not? No. Okay, because the constant is not 0. Actually, you don't know.
Yeah, okay.
Because you don't know LSB of the S1, right?
Yeah.
Okay. So let's say S1 is FF. Okay. That's assuming S1 is FF.
So,
Okay, it's FF. It's just adding another instruction on the top. Load S1, FF. Okay? And then do a test. What's gonna happen?
well, it basically, since it's being compared to 1, and it's ANDed with 1, all the other bits would go to 0 and it would just stay 1, right?
Yeah. So Z is 0, right?
Yeah.
Because T is not 0. That makes sense?
Mm-hmm.
Because T is not 0. T is a 8-bit. You can see. It's definitely 8-bit. It's a bitwise AND logic. So T is not 0. And that's why Z is 0, because 0 flag is not on. So Z is 0. What about C?
It would just be 0.
What does this do?
What's it?
Bitwise XOR.
Yeah.
Okay?
Oh, so then it'd be 1.
Yeah, it's like a what?
It's a
Parity bit check, right?
Yeah.
Or parity bit generator. It's odd number of ones or even number of ones in there, in T.
Is it an odd number?
Yeah, how many?
Just 1.
Just one, right? Just one in there. Just one single one in there. Why? Because this guy is FF, this is 0, 1. So eventually T becomes all zeros, but only the LSB is 1. So there's odd number of ones in there. And if you do XOR logic for each bit, eventually it's giving you a 1. Okay? So that shows you that there are odd number of ones in T. Okay? And there are some examples for this tutorial. Let's take a look.
Actually,
What's that?
are these the same flags as the flag register in like a traditional microcontroller? So like, are there also like the global interrupt bits and such?
Depending on which microcontroller you're using, right?
Yeah.
But I remember when I was doing assembly for the Arduino microcontroller, so use Arduino as well, right?
Yeah.
So the flag are just the global. They just one universal one.
Okay.
Yeah, they're being reused by other instructions. Yeah. So in that case, when you want to reuse it, you have to clear it. Okay, so like the interrupts. Every time you get an interrupt, before the end of the interrupt service routine, you have to clear it before you can reuse it, right? Because the flag is on. When the flag is on, you get into the interrupt, right? But by the end, towards the end of the interrupt routine, service routine, you clear that flag to enable the interrupt again. Just waiting for another, for example, like 10 milliseconds to get into it. Similar. Yeah. Let's look at the first example. So what is this doing? Just directly sending the switches values to the LEDs. fancy stuff. The very first example, directly sending switch values to the LEDs. Okay, how that works? You go to the code. That's in your main file. Remember, your main.v file is from the examples from the template file, and you include the core, and you include the ROM, which is generated by the assembler, and then you have to include a little bit of Verilog code at the bottom of the main file. So this is that part of the Verilog code. You plug it into your main file. Okay, and these are all from the template file. So keep in mind, you have to generate a new .v file and name it as main.v, and copy and paste all these kind of things from the template into a main.v file, like all these things, and change some of the parameters, because the example from the textbook used used the old version of the KCP core, okay, and make all these changes and include this piece of code at the bottom of the main.v file. So what this one does is it enables the write, and whenever the write is 1 is getting enabled, you directly send the value at the output port to the LED register. So that LED register was directly assigned to the LED, which is the physical LED on the board. So it's directly sending the output, whatever at the output, to the LED. The main file is directly interfacing with the LED by doing this, and your input is from the switch. So here is how you do it. You change the import. So .import, that's the import from the core. That's a processor. Can see the processor. And the processor's import is shorted to the physical board's SW. That's a keyword I've been using for so long, right? So SW is the switches. The switches are directly shorted to the import. So whatever you are doing with the switches will directly send to the import. So CPU takes it, and the CPU doesn't do anything and directly send it to the output. What a smart CPU. All right? So receive something and directly throw it to the LEDs. No computation at all, okay? So compile this little thing. I think that's the entire assembly code. You don't need anything else. That's a little instruction you can put into the ROM. And use assembler to compile it, and eventually generate this memory file. You can see all these files that you want to use for your design. Okay, and then it should work. And the textbook has a bunch of examples. For example, this chapter 16, list 02. I think you can download all the examples from here. If these files are not directly available in the folder, you can find the PDF version of it. But the thing is, you have to type it up yourself. So it's all provided on the tutorial, in the tutorial. So similar way to compile it is the assembler, right? In the command line, compile it. And followed by the first super simple example, there are a bunch of other examples let you do some computation, just very simple subtraction and addition, like this one. See, you can name the input port ID with a different name. So I'm just using 00. So the goal of that is, you can see the output command over here is also taking the port ID 00 as well. So in that case, if you do the input port ID and the output port ID to be the same name, eventually they'll be internally connected to each other. Okay, so it doesn't have to be 00 all the time. If you do 01 and 01 here, they will be shorted internal as well. Okay, and because the input, remember the input, is taking the input from the switch. So S0, that register is going to store any value from the switch. If you toggle some of the switches to form a different binary number, and that value will be directly sent to S0. Okay, and S0 is shorted to the port 00. And eventually that value will be sent to this port and sent to and you load S0 as the input from the switch to S1, and S1 will output the value to the same port. Okay, and you can do a little addition here. So 13 is a hex number. It's being added to S1 and eventually assigned back to S1. So you can change the value a little bit and do some computation with the CPU and send it to the port. What else? I can do a jump. Let's look at the jump here. Okay, let's look at this example. So what this does, you load different values to the different registers and do a test. Remember how test works? And if it's non-zero means it's a 1, right? If it's a 1, jump to testing. So it's a label here. And run this code and return back to the location where it jumps. Keep in mind, you can return back to here. Okay? And eventually jump to forever, so it's able to form a loop. Because assembly doesn't have a mechanism to run the code back and forth like the loop in Arduino. So you have to form a loop by yourself manually. So eventually after this one, you want to jump back to where then have to put a label somewhere. And more examples using the non-z, z, whenever it's non-zero, I have a label here. Whenever it's 0, I have a label here. Okay, so the tutorial has some basic examples, and for the lab, it's a bit more advanced. Let's take a look at it real quick. It may take some time, so I give you guys 2 weeks to work on it. But this is a lab starting from the week after next. Okay, so you have about 3 weeks to finish it. I think this is a divider or something with some computation over here. This is example from the textbook, but I made some modifications. So we will talk about this later. So expect that there's a lab, 2-week lab next week, or the week after next, okay? And followed by that, I'm gonna give you 3 more labs. And the first one is the ADC. There's an ADC module on the IPGA. And this was a course project from last semester. And I'm gonna use part of the code other people created and give you some tasks for this lab. And followed by that will be the 6502 SOC, and there will be another NDA contract for you guys to sign because that's from WDC, from that company. And we're going to use their core and to implement on a different IPGA platform. So you have the opportunity to work on a different platform that was designed by Intel, I think. It take another 2 weeks or 3 weeks to work on that one. Then that's everything for the labs for this class this semester.
Okay.
And for the lectures, there are a couple more things to cover. So after the software core, there will be a sequential circuit design, which is important to deal with all these different states, build state machines, because that will be used for the following 3 tutorials, including the UART, USB, and SPI. So you probably have used the UART for some of the microcontroller platforms. It's basically just RX and TX. So we used the library from in C for the microcontrollers for the communication. But for the UART we are going to do for this class, will be the bottom level timing diagrams. So you have to program the controller yourself, like what you did for the VGA controller. And in that case, you can program a little UART controller with RX and TX in the IPGA chip, and can directly interface it with the standard UART interface from the microcontroller. So that's the goal for this tutorial. Similar to the USB and SPI, okay? So the SPI is a very popular port being used for example, the SD card and a couple of different digital sensors that's becoming super popular. And so we will be able to learn the bottom level protocol of the SPI as well. And you will be able to put these kind of protocol or kind of skills in your resume after this class. So adding a couple of lines over there, for example, the UART protocols, right? And also the SPI protocols, and experience with designing a little digital sensor to interface with a commercial module. For example, this one we're dealing with a digital sensor like this. Okay. So in the future, you can imagine if you know how to program the SPI, it's going to be very easy to design a digital sensor and sell it in the future. It's basically just a digital module with a port and maybe a little ADC in there as well. If you know all these, how to program all these Verilog modules, and eventually you put everything together, you synthesize the design into the IPGA block, and eventually it becomes a digital sensor you can sell. Okay. And followed by a course project. So I'm going to think about that, what we are going to do for that. It will be something with the 6502 SoC, I think. I will let you guys know later. Okay. Any questions on anything? So we'll talk about more about the bottom level ports and timing diagrams from the core on Tuesday next week. Hopefully, I'll give you guys more time on Thursday instead of covering new stuff on Thursday. I'll probably just let you guys work on the assignments. There are a lot of assignments accumulated. Yeah. All right, you can start working on your assignment. I'll give the time to you guys. Can turn in that in-class exercise to earn that 3 points.